What I would like to do now is look at regression in general context and some potential shortcomings along with their corrections. So go ahead and open up a new Colab notebook. And what I want you to do is maybe title this one, well, I guess we can just title it Regression Models. And go ahead and I want you right now to open up the California housing data set and split it into X and Y, just like we did before, okay? I want to see, can you do that on your own at this point? It's great if you can. If you're a little unsure, you can't always copy the code that we did before, or you can follow along with me as I move forward. Okay, but I encourage you to really get that head start. Try it on your own. That's how you're going to learn the best. It's great if you're a step ahead of me, then my words can just fall into the background. So I recall that that data set lives here in the file folder. So I click there. And then under sample data, I've got this California housing train.csv. And I want to click on the copy path. Okay. And I can X out the file area, import pandas as PD. Then df equals pd.read underscore csv. In quotations, I can put the file path, Command V. I do always like to check it and make sure it is what I think it is, so I copy it correctly. And so I run that and it looks good. Now I want to set my X and Y. So for X, that's going to be df.iloc, I'm going to use index location, okay? Take all rows, that's a colon, comma, to get all columns, I set another colon, and then go up until the negative first or the last row. And then Y should be similarly df.iloc using index location, brackets, all rows, comma, negative first or the last column. Okay, so that establishes X and Y. And then I'm going to go ahead and give the header up here at the top, using little arrows and clicks, and call it just loading data. Load Boston out. Sorry, Boston housing is another famous one. Load California housing data. That slide may have been Boston housing, I'm not sure. It was a little different. So, okay. What are we going to do next? We're going to go ahead and build the machine learning model. Okay. So let's do it all. This is review. Build machine learning model. I'll give a little header here. Text header. And I'm going to put all in one cell. Okay, so I've got from sklearn.linear model, import linear regression. Okay, then you want to initialize your model. Model equals linear regression. Then we're going to do model.fit on x comma y. And then model.score on x comma y. Isn't that amazing? It's only so many lines of code, right? There's power in those lines of code. Make no mistake about it. Now we're going to run that. We get the score of 0.64. Okay, here's what I want to do. That was our review. I want to do a different regressor. Okay, there are many regressors. Regressors are different kinds of machine learning model that belong to a classification of models that's called regression. And we will take a look at different classifications, and primarily regression and classification, or regressors and classifiers. Let me put it like that. So what's another regressor? Let's just do one. I don't want to go in depth with it, but I will tell you there is in the tree library a decision tree regressor. Go ahead and import that now. Note if I type it correctly, when I start typing it, right, I get that option. I can click to it. So what is this? Decision tree is like a game of 20 questions, okay? And so basically what it's going to do is say something like, if you look at the data, hey, if the total bedrooms are greater than 1,000, then go to this branch. And if the population is less than 1,000, go to this branch. And then there's always an otherwise, go to this branch. And so it branches out into all these leaves, and the final leaves are the predictions. Okay? So it's like a game of 20 questions, and we can look at that in more depth later. What I want to do now is just treat it as a regressor. Say, hey, it's going to work like linear regression. We can set it up in the exact same way. The difference is that it's just a different model. And so it's going to give a different score because it's going to fit the data differently. And it really is like a splitter, like it asks questions. And it's just totally different mathematically, but it has the same goal, you know, the goal being kind of to use weights and sum to get the results. So you see how everything there is the same? And this is the beauty of the system. We could easily write a function to do this. We import a different regressor. We initialize it. And once you define model as some other regressor, any machine learning model, then it's always going to be model.fit, and you can do model.score afterward to actually score it. Okay, so let's see what we get. Oh my goodness, we got a 1.0. What's going on here? Machine learning is amazing. It's incredible. Or maybe it's a red flag. Why a red flag? Anyone have any ideas out there? I'm always skeptical when I get 100% of machine learning. Almost every time it's not good. There's something is awry, something is missed, or something is unexpected. Okay, why? Well, first of all, 1.0 is the goal, okay? Don't get me wrong. But what's the goal of the machine learning model? Is it really to get perfect predictions on the data that it's training on? Well, yes and no. It is, but only in the context of making good predictions for new data that's coming in. Now you might think, well, hey, if it gets better predictions, how could it not predict better on new data? Let's try it. Let's see. So if you click on files, there is a California housing test data set. Note that it's also a CSV file. So let's go ahead and load this in now. Okay, we're going to load it in the same way, but instead of calling it X and Y, we're going to call it X test and Y test. Okay, that's the only difference. Okay, furthermore, it's in the same location, so it has the same path. So I'm going to show you what I'm going to do. Instead of like recopying the path here, which I could do, I need all this code. So I'm just going to copy it up here. Okay. I think I'll go ahead and put in a new text header. Let's do this with me. Load California test data. Okay, we're going to test it. All right. So what I can do is just change the word train to test. And I do want to verify, make sure that it both loads and that it is different by looking at it. It should be a different data set, but the same data frame, I mean, same like columns is what I mean, but different values. So let's check. The last median house value here is 344,700. If I scroll up to the other one, yeah, those are different, right? 669,000. Now I called it DF again, which I shouldn't have done, but whatever. The point is that we can do X and Y differently. And once again, it's the same, but we're going to call it something different. We're going to call it X test and Y test. So X test, Y test. And so basically, what's the idea? The idea here is that we're going to see how the machine learning models do on the test data, on data it has never seen before. Okay? And the reason why this is going to be great is because we know what the answers should be, right? The model won't know it. The model's only going to look at X test, okay? But we compare it to Y test. You know, okay. So it has to do with the score here, right? Let's do it with code, okay? I'm going to do some copying and pasting this around. So just recopy this. I think I'm going to make these subheaders. So underneath a subheader would be 2 hashtags. So build regressors. Well, sometimes I'm not sure about the headers. Build regression models. I'll just say that for now because it's with it's underneath the testing data. And you could add that if you want, and score and test data. All right. So let's look at the differences. So we're going to do the same import. And again, I only do that. You don't have to re-import it. It's because so that when you copy chunks of code, you have most of it there. Initialize the model the same way. We're actually fitting it the same way. Okay, we're still training it. This is on the training set actually. But now when we score it, change this. Change this to X test and Y test. Okay, the beauty of this now is that the model was trained on just regular X and Y, the training set. But now, when we score it on the test set, what it's going to do is going to deliver predictions on X test, and it's going to compare them to Y test. So let's see what we get. 0.6195. If you go back up and compare, it's a little less, right? It's a little less, okay? Similar, but a little less. So, okay, before I say anything, let's try it with the now decision tree regressor, okay? You could write it afresh. You could copy it here. You could copy it in the other cell that we just did, right? So again, first 3 lines are the same. The only real difference is it should be X test and Y test. Again, I really want to emphasize this point because it's really important. We're fitting the model on the training set, X and Y, okay? This X test is different. So once we do score, it's basically making a prediction. It's the model's making a prediction and it doesn't know. We don't know what it's going to do, but it has known results. So the known results are Y test and we get to see how it did. Okay, so let's try that now with the decision tree regressor. Go ahead and do that and see what you get. You guys will think, what do you think you'll get? I mean, we got 1.0 before. Will it also be not quite as good, like a 0.9 or what? 0.655. Not even close. Like, it's way off. I mean, when I say way off, hey, it beat linear regression by a little bit, but it's nowhere near the 1.0, right? That appeared to be perfect prediction. See, there it is. 1.0. What the heck is going on here? Can anybody tell me the issue? In fact, if you're watching this right now, I want you to, in the chat, state what the issue is if you know, or if you think, if you have an idea, okay? Like why is linear regression close, but decision tree is like totally different? And I'm going to tell you this. It gets into a subtlety of machine learning. And there's like a trade-off. And to emphasize this, I have some slides, okay? These are from, by the way, the author of Hands-on Gradient Boosting with XGBoost and Scikit-learn. That's a book published by Pact. It has a GitHub page. And I go over this in detail in the 2nd chapter of that book. This book, by the way, is targeting really like adult students who already know Python, who are ready to get into machine learning. But any of you could try it after, this machine learning class. I mean, it's not targeting students, though. I just want to mention that. It is on Amazon. To show you. If I just type in XGBoost, I believe it was the first book in print in XGBoost. It should show up. Yeah, there we go. Doing well, too. See, that's me. 5 stars. All right. Okay. That's not the point. The point is, I'm just showing you where I got it from. Okay, so imagine you have these different points. Okay, these are the data points. And this is what we've talked about. Hey, this is a regression line, right? That's the line of best fit, right? There's some above and below. You can only get it so good. And that's why linear regression sometimes only does so well, because, you know, you cannot get a 100% on this. That's as good as you get. I don't even know what that is. It's probably like 0.4 or something. Okay, now let's look at an 8th degree polynomial, because I can say, well, what if I make an 8th degree polynomial? How well can I fit it? Well, you can fit it perfectly. Okay, no matter how many points you have, there's always a polynomial of one higher that you can use to fit it perfectly. So how's it going to do with predictions? Well, it's going to predict on the pink curve. So if you look between, let's say, like this 3 and 4, value 3.5 may give you a pretty good prediction. But look at some of these other points. Between 1 and 2, and you're getting something way off the charts. Between, looks like 8 and 9, 2, you're getting something way down, let alone over 9, way up. And so these are going to be off on a lot of predictions. This is what you call overfitting the data. Okay, the model has overfit the data. It's not going to generalize well. Decision trees can be like this. Because it's a game of 20 questions, you can make a game of 20,000 questions or 20 million until you get every little dot perfectly circled. But there's some crazy path to take to get there, and it's not going to work well on other data points. Okay, so in general with machine learning, you're trying to find a balance, and you can achieve that here a little better with, say, a 3rd degree polynomial, where, I would say that the data points are closer, but importantly, it's generalizing well to like new data points. Okay, and that's the goal of machine learning, to generalize well to new data points. Now, for us, right now, if we go back to the scores, we need to address this issue, right? And here's the issue. It happens to be really nice that they have split this into a training and test set for us. Note that also the case in NIST. But as you know from the data that you've looked at before, that usually is not the case. You need to do that. And so I'm going to show you the code now, how to do that. Now it could be with any CSV file, and I'm going to do it with the training file that we already have. Okay, so we're going to do train test split together right now. Let's give a new header in, call it a train test split, and let's just take it from the top. Okay, and once it's from the top, this would be like what you were doing if you were doing your own data set. And so I'm copying the first info. If you're sure about your data set, you don't technically need the header, but I think it's nice. And for X and Y, well, I'm going to go to the top. Look at all this copying and pasting. Shouldn't be doing that. I honestly do it sometimes. Okay, so there's a loading of data, and if you want to do a quick check, you can, like again, run df head. I don't like to overdo df head, but I also do like to look at the data. So this is all just standard. Load data. It's nice when it's all in one cell, right? It's a little out of order, but whatever. When I say it's out of order, we're just showing to verify that the data is what we think it is. You can say confirm data. Confirm df, right? Okay, so that's all loading up. That's not train test split. So now we're going to split it. Okay? So how do we do that? Well, let's do it like this. Type with me, sklearn.model_selection, import, train, and there it is, train test split. Okay? I'm going to give little comments in here. So import train test split. And now we split the data into a training and test set. Okay, so how do I do that? Well, I feel like it's the equivalent of a mouthful because you got four pieces, okay? You got X train, comma, X test, comma, Y train, comma, Y test, comma. And those all equal train, test, split, And then what are we splitting? It's x comma y. So all this is, not c, x. All this is doing, it's taking x and y and splitting them. That's it. But it does it in a way, I think usually it's taking 80% is the training data and 20% then is the test data. I think that's the right order. When I say right order, because is it X train, Y train? I think that's right. So from there, let me just go ahead and run it. And then let's try it using this. Now, just so you know, this is different than the test set that they have made for us that we already looked at. What we did is we split the training set further and made like a new test set. That's actually good practice to do that because you can then keep tweaking the model and making adjustments on this, and still there's data it's never seen before. Okay, so let's go ahead and just do it one more time using then this new setup. So you can write it afresh, or you can copy it. It's okay to copy code. And the difference is it's going to be X train and Y train. Okay. So, there you go, right? Everything else is the same. So we import linear regression, we initialize it, we fit it on the training set, see, but score it on the test set. Okay, so hit Shift Enter there, get 6.355, and I'll show you, I don't usually copy and paste a bunch. I will type in sklearn, try it with me, .tree, import decision tree regressor, model equals decision tree regressor. I'm initializing the model there. Now I'm fitting the model, and importantly, when I fit it, it's on the training set, right? X train, Y train. Now I've got a totally different test set to score it. And I get a very comparable 0.639, right? They're closer here. So let me just address a potential question or two. Number one, so how do you improve the score? Well, one way is to fine-tune hyperparameters, which is an advanced topic, which we're definitely not going to get into today. I will try to include some extra videos on that at some point. Another is that you can actually try different models, right? So this is a regression data set, and any regressor will work. Well, let's try one of my favorites. Hands-on gradient boosting with Xgboost, and scikit-learn features Xgboost. So it's do this with me, from Xgboost, import XGB regressor. Okay. And then, see, once you do that, then the steps are basically the same. See if you can do it. See if you can follow the pattern here and do the same steps. Right? We've got model equals, it's what you import. So just start typing it in. We're hoping, there Colab goes, finding it for us, press return, put in the parentheses. The other two lines are the exact same then. Because it's just that the initial model is different, it's done differently. Now, you're hopefully wondering, what is Xgboost? And, I wrote like hundreds of pages to answer that question in a book, but to tell you as simply as possible, it is an ensemble of decision trees, okay? And the difference is that what it does, it doesn't just take the trees, it learns from the errors of the trees. So it learns where they go wrong, okay? And it's a pretty unique model in that sense, gradient boosting is, and it's state of the art. And let's see how it does here. And this is where it can start to get fun, right? You try different things and you see what's the score. Got a warning, 0.78, look at that, right? Way better, it's a superior model, right? You can imagine what's better, one decision tree, or like Xgboost is by default, it's 100, right? 100. Let me give you another regressor to try. Random forest. Random forest is also a lot of decision trees. The difference is instead of training on the errors, it actually takes the averages of them and it uses some random traits, it's important. The random piece is important because if you just had all the same decision trees, you get the same result. So there's got to be randomness to get different types of decision trees. So from sklearn dot ensemble, I believe, yes. Import random forest regressor. You could try any regressor. Model equals random forest regressor. And then model.fit on X train and Y train. I don't know about you guys, I'm feeling like writing a function here. And we will start using functions again. Because it's a great way to compare models without having, well, anytime you're copying and pasting code, you write a function. Model.score X, X test Y test. Let's see how it does. It's taking a moment, right? I mean, you know, it's building like 100 machine learning models. Each of these models are training on like 70,000 rows. These things are blazing fast. Look at that, it beats Xgboost. Wow. So a random forest regressor is doing the best with this particular data set. Different models will perform differently on different data sets. By the way, I did see, just for the fun, I want to try the XGB random forest regressor. So if I go, you know what, I can't take this anymore. I'm going to write a function. Do it with me. Def. So you got to get the model in here, right? So what are we doing? We're just like scoring. We'll call it regressor. It's a regressor, but the input should be a model, right? And then what we just do with the model is, I was wondering if there's a way to do the parentheses, but I think, yeah, I don't think so. I think what we want to do is just model.fit X train, Y train, and then maybe just even return model.score X test, Y test, right? Let's try it, okay? So run that, type it in regressor, and now let's try one that we've already done to see does it work. By the way, these have some randomness involved, so you could try it again and see does it give a different score. So let's try the random forest regressor. Yeah, I get a comparable score. Okay, what I wanted to try was this. So you can also, from Xgboost, I saw it in there, import Xgboost has their own random forests. Okay, they're a little different. That's what the RF stands for, the random forest, right? So it's a random forest, and when you get a random forest, a bunch of decision trees going to take average using their own algorithm. Yeah, these are mathematically sophisticated, but what's nice is that you don't have to XGB is an RF regressor, not RGRF. A bit of a mouthful. What I was saying is you don't have to worry about the mathematical details. You just, a lot of machine learning is, it's experimental. You try it, and if it gets you better results, you go with that. Okay, here we go. Not nearly as good. 0.537. That would be the worst one yet. You know, I've gotten good results sometimes with that one, but not often. You know, they're definitely known for their regular regressor and classifier and for working in very big data. They've won a lot of machine learning competitions, XGBoost. Okay, so you get in here, not just regression models. Let's go ahead and also add something very important. Train, test, split. Okay, you now don't know about the difference between a training set and a test set, in addition to a lot of regressors that you can use on your own data sets. When you're going to work on your own here, note that these regressors will only work for certain types of data. If your output, what you're trying to predict, is all like zeros or ones, yeses or nos, or like even red, green, blue, you need a different type of machine learning models, really, which are classifiers. And we'll look at those soon.